Have you ever wondered how your computer actually remembers things? Or why certain hardware terms we use seem to completely contradict themselves? Today we are decoding a fascinating mystery right at the very heart of computer memory. We're going to demystify the core components, RAM and ROM, and tackle what I like to call the read-only paradox.
So let's just dive right in with our central question. If EPROM is read-only memory, how in the world are we able to write to it? Now, this exact paradox actually sparked an incredibly lively and honestly brilliant thread on the Electrical Engineering Stack Exchange. And it's a fantastic question, right? If something is strictly designated read-only, writing new data to it should be literally impossible. Yet our modern devices write to these chips all the time. So what's going on?
To understand why this happens, we first need to look at the fundamental roles of memory. Imagine your CPU, the brain of your computer, is you. ROM is your permanent bookshelf. When the power goes off, the book stays safely on the shelf. But you can't read a book while it's sitting all the way across the room. You need to pull it down and put it on your desk to actively read it or work with it. That desk, that's your RAM. It's your active workspace. When you're done studying, or if the power simply goes out, the desk gets completely cleared off.
RAM, or random access memory, is that active temporary workspace. It is inherently volatile. That means it completely loses its data the very second it loses electrical power. But the trade-off is incredible speed. It delivers the lightning-fast read and write speeds that your CPU absolutely relies on to juggle multiple applications at once. Basically, the more desk space you have, the more apps you can keep open for seamless multitasking without your system grinding to a halt.
Now, this need for a temporary workspace gives us two primary types of RAM, static RAM, or SRAM, and dynamic RAM, or DRAM. SRAM uses bistable latching circuitry, specifically things called flip-flop gates. It's unbelievably fast and relatively expensive, which makes it perfect for small amounts of CPU cache memory. Then we have DRAM. This is the main memory you usually buy in huge gigabyte chunks for your PC. DRAM is a bit slower and a lot less expensive because of how it stores data. It uses tiny electrical capacitors.
Now think about the number 1 for a second. In DRAM, a single tiny capacitor is used to store just one bit of data. Because capacitors naturally leak electrical charge over time, that data would just vanish if left completely alone. To stop this from happening, DRAM requires a dedicated refresh circuit. This circuit constantly pumps electricity back into those capacitors just to maintain the ones and zeros. It's an active, constantly refreshing process, which is exactly why we call it dynamic RAM.
So, transitioning back from the active desk to the permanent bookshelf, we can really clearly see the divide here. Unlike RAM, ROM is non-volatile. It holds onto its data even when the power is completely cut off. While RAM is fast, volatile, and actively read and written to during normal usage, ROM is traditionally slower, smaller in capacity, and, well, primarily read-only. It holds the essential, permanent instructions your computer needs just to boot up and initialize its hardware.
But here's where it gets really interesting. ROM isn't just one static, unchanging piece of technology. It's actually an entire family of chips that have evolved massively over the decades to meet some highly complex engineering challenges. The rigid definition of read-only started to bend as engineers realized they desperately needed ways to update a computer's permanent instructions without having to rip out and throw away the entire physical chip.
Looking at the timeline of innovation, we started out with mask ROM. This was programmed directly by the manufacturer at the factory, completely hardwired and utterly unchangeable. Then came PROM, where the user could write to it exactly once. Next up was EPROM, which you could erase using UV light. And finally, EEPROM, which could be erased electrically. Every single one of these steps was a massive technological leap, designed specifically to make non-volatile memory more flexible and forgiving for developers. Let's look a little closer at those early hurdles. Mask ROM was incredibly inflexible, so engineers came up with PROM, or programmable read-only memory. You could buy it entirely blank, just filled with ones, and use a special device called a burner to write your data by literally applying electrical charges to the pins. But there was a massive flaw. It was a strict one-time process. If a developer made a single line of code mistake while burning a PROM, the entire physical chip literally went straight into the trash. So how could engineers possibly solve the incredibly expensive problem of a write-once chip?
Well, they solved it with EPROM. But the solution was honestly a bit wild. To erase an EPROM, you literally had to expose the chip to a strong source of ultraviolet light right through a tiny quartz window on the top of the device. This effectively reset the entire chip to be blank again.
There's a great quote from a Stack Exchange user discussing this evolution, pointing out that later tech saved, quote, a lot of time by not sitting your device in a tanning bed each time you want to reprogram it. It's funny, but that is exactly what early software development required.
Which brings us to the hero of our paradox, EPROM, electrically erasable, programmable, read-only memory. Finally, engineers had a chip that retained its data when the power was off, acting just like that traditional ROM bookshelf, but it could be selectively erased and rewritten, byte by byte, using electrical signals right there on the circuit board. No more UV canning beds. But this brings us right back to our central paradox. If we can electrically erase and write to it under normal program control, why on earth do we still call it read-only memory?
The real breakthrough here is that we have to fundamentally redefine what ROM means today. As the Stack Exchange experts clarify, EPROM is heavily asymmetrical. Reading data from it is lightning fast and unlimited, just like reading a normal book. But writing to it, writing is vastly slower. We're talking orders of magnitude slower than writing to RAM. It requires different operational modes, sometimes extra voltage, and the chip actually actively wears out after a certain number of write cycles. You physically cannot use it the way you use RAM for real-time active multitasking.
So, it turns out keeping ROM in the name was actually largely a marketing strategy. Back in 1972, changing a hardwired mask ROM meant spending thousands of dollars at a factory. When Intel introduced programmable versions, their pitch was essentially, hey, this acts just like your permanent ROM bookshelf, but you can actually change the books yourself. The name EPROM stuck because it perfectly described the chip's evolution to engineers at the time. So yeah, you can basically blame 1970s marketing for the confusing acronyms we're still stuck with today.
Now, modern flash memory, like the solid-state drive in your computer or the storage inside your phone, is really just a highly advanced evolution of this exact EEPROM technology. It allows for erasing and rewriting in much larger blocks rather than just byte by byte. As flash and emerging technologies like non-volatile RAM continue to blur the lines between the permanent bookshelf and the active desk workspace, we kind of have to wonder, will the rigid terms RAM and ROM eventually become a thing of the past? That's a really fascinating thought to leave you with, as our technology just keeps outgrowing its own vocabulary. Thanks for joining me for this explainer.